Hi, everyone, and welcome back. It's Kira Garfolo with Math 155 at Greenville Tech. Today, we're going to finish Unit 3 by talking about compound interest in Section 3.6. Remember back a couple sections ago when we learned about simple interest, and remember that we only paid interest on that principal amount over a certain period, okay? So, for example, if we invested $1,000 at a 12% rate, then simple interest was that I equals PRT formula, and we'd see that we would get $240 at the end of 2 years. In this case, no interest accumulates over the time. They don't pay us a penny of interest until the very end of that 2 years. More commonly, we see interest accumulating during the periods. That happens for loans when we owe money, and it also happens when we invest money into savings accounts and other types of interest-bearing accounts. So when interest accumulates each period, it's going to be paid on the original principal plus any interest that has already added. So if you're earning interest each month, then each month, assuming you're not making any other withdrawals or transactions, you're going to be getting paid a little bit more because you're going to be getting paid on that accumulating total. This is what we refer to as compounding. So let's say now that we're going to invest that same $1,000 at an annual rate of 12%, just like before, but now we're going to be compounding it annually. So instead of just getting money at the end of 2 years, we're going to get interest 12% every single year. So at the end of our first year, we're going to have 1120 total because we're going to get 120 in interest at the end of the first year. So then at the end of our second year, we're going to get 12% on that amount instead of just on that original $1,000. So now instead of making $240 in interest, we're going to make that $254 because now at the end we're going to have $1,254.40. That is because it is accumulating during the life of the loan and not just simply being paid out at the end. Now, the way that we just calculated that by looking at the end of the first year and then looking at the end of the second year isn't the most efficient, but it works okay for annual compounding, especially if you're just doing a couple years. You guys can do that calculation 2 or 3 times, no big deal. But what if you're doing it in other terms? What if you're going to be doing it, let's say quarterly or monthly or semi-annually or maybe even daily? That's going to be very, tedious, let's say, mathematically. So we'd have to split up our interest if it wasn't annual because you're not getting, 12% a day. You'd be getting 12% divided by that 365 a day. And that would it just gets really ugly really fast. So instead, there is an easier formula that we can apply. And the formula that we're going to use for compound interest is this. And again, remember, this part is just the explanation. This is the formula that you need. So here, A is the amount at the end of the time period of interest. P is the initial amount. R is going to be that interest rate. Remember, it has to be a decimal. N is the number of times per year that the interest is paid. So remember, semi-annually it's paid twice a year, quarterly 4 times a year, monthly 12 times a year, daily 365. I guess weekly you could have 52 times a year, things like that. The same numbers from the previous lesson. And T here is going to be our time in years, just like in simple interest. Let's look at an example here. We're going to use the same numbers from before where we invested $1,000 at an annual rate of 12%, and we were investing it for 2 years. We want to know our balance after 2 years if it's compounded annually. So we're going to use this formula to verify what we got, doing it kind of the harder way. Quarterly, monthly, and daily. So let's start here. Annually, we're going to have A equals P, which is going to be $1,000, times 1 plus our rate is going to be 0.12. Annually, we're just doing it 1 time per year. And then 1 times 2. And that is going to give us $1,254.40, which is what we found earlier, so good. quarterly. We're going to do the same thing, have the same formula, except now it's going to be 4 times a year. So instead of being 1, we're going to replace that with 4. And it's still going to be 2 years. So we'll plug that in and we'll get 1266.77. So we see that annually we made 1254. Quarterly, we're actually making more at 1266 and some change. If we want to do it, I'm going to come up here. Monthly, we do the same exact formula, 1,000 times 1 plus 0.12, but now we're doing it 12 times a year. And that's going to give us 1269.73. And daily is going to be 365 times a year. So we're going to have 1,000 times 1 plus 0.12 still, but now 365. And that is going to give us 1271.20. So you can see that the more frequently we compound, if we don't change anything else, more frequent compounding is going to give us a little bit more. Annually, we were getting 1254, and if we did it as frequently as daily, we were getting 1271. So what is that, about 16 bucks, 17 bucks difference after the end of the 2 years. This is a great place to pause and make sure you can use this formula to get all 4 of these answers. You're going to continue to see it. Now, pause again and work this problem. I'll give you a moment and then I'll go on with the problem. So, what will be the amount if $1,000 is invested at 6% interest compounded monthly for 5 years? Monthly, we're going to do 12 times a year. We're starting with $1,000. Our interest rate is 6%, and we're doing it for 5 years. So remember that we have that formula that you will be given on the test. A equals P times 1 plus R over N to the N times T. So we are investing that initial $1,000. And our interest rate is 0.06 as a decimal, 12 times per year for 5 years. Now plug this into your calculator carefully. These are other common things. I really like math print in these cases. Make sure that it looks just like this. And if you plug this in, you're going to get 1348.85. If you do nothing and you just put $1,000 in an account that earns 6% interest and it's compounding monthly, at the end of 5 years, you'll have $1,348 and some change. So not bad. How much did you gain? Almost $350. This is why investments can be wise over the long run. Investing young, I'm sure everyone's heard that. Investing young for retirement is way more advantageous because your money works harder for longer. It's going to continue to build over and over and over time, and that will add up quickly by the time you're ready to retire. Now, if you want to calculate the total interest paid, we don't have a simple formula like I equals PRT when we're dealing with compounding. However, we just found how much we were going to end up total, right? And we know how much we invested with to begin with. So we can just find the difference in those to find how much our total interest was. Okay, so difference in the ending amount minus what you started with, and that's how much interest there was. So it is still a relatively simple formula. It's just not a formula on its own. Okay, so let's take a moment and practice. Let's say that a business invests $50,000 at 10% interest compounded daily for a period of 1 year. How much interest did they earn? Well, first we need to calculate how much it's going to be worth at the end of a year. So to find A, remember that we're going to use that calculator or that formula, P times 1 plus R over N to the NT. So that's going to be the $50,000 that they started with. 1 plus their rate is 0.10, because remember we need the decimal version. They're compounding daily, so N is going to be 365 in this case. and they're doing it for 1 year. And if we calculate that out very carefully in our calculator, we're going to see that at the end of the year, they're going to have $55,257.79. Okay. Now be careful. That's not what the question asks. That is not how much interest they earn. That's how much they have at the end. So the interest earned is just going to be what you had at the end minus what you had at the start, which is going to be your A minus your P. So you're going to have that 55,257.79 minus the initial 50,000 that they put in. So you're going to see that they got $5,257.79. That's how much interest they earned in a year of compounding daily at 10%. Okay. Now, sometimes we don't want what it's going to be worth at the end of the period. We want to know how much we need to invest on the front end to have that amount at the end of the time. So for example, what salary in 1960 was equivalent to a salary of $50,000 in 1990, assuming that there was an inflation rate of 6% per year? So we're going to use the same exact formula as before, but remember that A is always going to be the later one. So this is going to be the 1990 amount. This is what it was in 1960, not 1600, goodness. Okay. And then everything else works the same. We know that the salary later, it's always a good idea to know that A is going to be later and P is going to be earlier. So in whatever context of the problem, A comes after P, okay? So here 1990 came after 1960. So A is going to be our $50,000. We don't know what P is. We want to know how much we would have to have made. We know that we're going to count 6% per year, so 0.06. Yearly inflation, so yearly is going to be once per year. And we're just going to plug this in our formula. Okay. We know that $50,000 is going to equal P times 1.06 to the 30th. And if we just use algebra to solve for P, we see that that salary would have had to have been $8,705. So that stings a little bit, right? If let's say your parents, your grandparents in 1960 made $8,705 a year, that would have been equivalent to making $50,000 in 1990, assuming a constant 6% inflation rate. There is an assumption there. Okay, let's look at another example. How much do we have to invest at 6% compounding quarterly? So remember that's going to be N is 4, in order to have $30,000 in an account 15 years from now, assuming that there are no withdrawals. So you're not taking any money out. You want in 15 years, so A is going to be 30,000. You want to know how much do you have to invest? So our A is 30,000, our R is 0.06, T is 15 because we're doing 15 years, and N is 4 because it's quarterly. Plug this in, pause for a moment, and solve for P. You should be able to get the answer of $12,278.88. If you need help with that, you can see that $30,000 is going to equal P times 1 plus 0.06 over 4 to the 4 times 15. So P is going to equal that 30,000 divided by 1 plus 0.06 over 4 to the 4 times 15. That's going to give you $12,279-ish. So if you are able to get a quarterly compounding account that's going to pay you 6% interest. If you put $12,279 in today, in 15 years, if you don't touch anything, you'll have $30,000. Now, we've kind of alluded to this already, but inflation occurs when prices of goods or services increase from one year to the next. It's been a hot topic in the news lately, so you guys are probably no strangers to this. Basically, it's saying that things cost more now than they did a year ago, or things will cost more next year than they do right now. Okay, as time goes, things cost more. If there's inflation, that also means that the same amount of money that you receive in the future is not worth as much as it is today. So for example, if you had $200 today, then in 2050, it's not going to be worth as much. It's the same $200, but you can't buy as much with it because money is not worth as much, okay? The same idea applies if we look back. $200 today, yeah, it's not nothing, but it's not as much as if somebody handed you $200 in 1950. That would have been a lot more money in 1950. Inflation uses the same principle as compounding, okay? You can think about it over the year, okay? Each year, if that cost is going up, then it's going up from what was the previous year. So it started, and then it went up some, and then went up from there, and then it went up from there, and so on. It's building upon itself, so we say that it is compounding. We typically speak in inflation as the amount annually, okay? So what is it compared to the same time last year? So we're going to typically assume that n equals 1. This is going to make our formula a little simpler. You can always still use the same formula, A equals P times 1 plus R over N to the N times T. Okay, and you're going to plug N equals 1. You can just use that directly. If you like to derive formulas, you can also pretty easily see that this is going to come out to be 1 plus R to the T. Okay, because N is 1, and so it's just going to, 1 times something divided by 1, it doesn't change those values. So as long as we know that we're talking annually, we can have that. For example, if we assume an inflation rate of 4%, so 0.04 over the next 10 years, so T is going to be 10, what will a salary of $30,000 today, so today, P, need to be 10 years from now, the future, to keep up with inflation? Okay. So we're looking into the future. The future is going to be A. P is what it is right now. We're talking about annual, so we can use that simplified formula. So 0.04 to the T. Okay. 10 years, so T is 10. If we plug this in, $30,000 times 1.04 to the 10th, we see $44,407. So in 10 years, assuming a 4% inflation rate every year, in 10 years, you will need $44,407 to buy the same amount of stuff as you would with $30,000 today. Kind of depressing, isn't it? Let's look at another example. What is the present value of $4,000 to be received 5 years from now if inflation is assumed to be 3% per year for the next 5 years? So we know that 5 is going to be our T. Okay. Now A and P are what we have to figure out here. We're looking for the present value. Okay, so we are looking for P. And we know that we're getting $4,000 in the future. So that's going to be our A. So A is the future $4,000. And P is what we're looking for. Just like before, we can solve this out. There's a little bit of algebra involved. We have to isolate P. So we're going to divide out here. And we're going to see the P is 3450 and some change. So if you invested, let's say 3450 at 3% per year for 5 years, at the end of those 5 years, you'd have $4,000. In terms of inflation, if you had 3450 today, then you would be able to have that would be worth the same as $4,000 in 5 years. Now, I want you to pause here and get some practice. If the inflation rate is 2% over the next 5 years, what will a salary of $25,000 today need to be 5 years from now to keep up with inflation. So we know today, and we're talking about the future. The future is always, the later one is always going to be A. So the future is what we're looking for. We know that we had $25,000 today. Trauma inflation, so we can use that simplified formula of A equals P times 1 plus R to the T. That's hard to see. So 25,000 times 1 plus 0.02 to the 5. And if we solve that out, we're going to see 27,602. If you make $25,000 today, in 5 years, assuming an inflation rate of 2%, you are going to need to make $27,602 in the future to be able to afford the same exact, to basically make the same relative amount. Now, using the same numbers from above, what salary in 1975 was equivalent to a salary of $60,000 and $2,000? Well, be careful with your A's and your P's here, okay? P is the one that's further past, A is the future, or the one that's later. So we know A here. We know $60,000 equals some salary. The inflation rate is 2%. And now what is our time? Well, now we're talking about 2000 versus 1975. So we're talking about a difference of 25 years. So if we move this around, we're going to see that we can get P is going to be 60,000 divided by that 1 plus 0.02 to the 25th. Which is going to give us 36,572. So if you made, assuming a 2% inflation rate every year, if you made $36,572 in 1975, the equivalent salary, or the salary to afford all the same cost of living things, in 2000, you would need to make $60,000. So in that span of 25 years, look how high that went up. Okay, let's try one more. What is the present value of $10,000 to be received 10 years from now if inflation is assumed to be 3% per year for the next 10 years? So we know we're dealing with a time of 10 years. We know we're dealing with a rate of 0.03. And our present value is what we're looking for. What is P? Okay. And you know that in the future, you're going to get $10,000. So this is going to be your A. So we can solve 10,000 equals P times 1 plus 0.03 to the 10th. So 10,000 divided by 1 plus 0.03 to the 10th is going to give us P, which is going to give us 7,441. So today, $7,441 is worth $10,000 in 10 years. And remember, you can think about this in terms of interest. If you put $7,441 into an account today, assuming a 3% gain inflation per year, don't do anything else, then in 10 years, it's going to be worth $10,000. Now, if you haven't picked up, this whole unit has a lot of applications to daily life, and this section is no different. So a lot of our financial decisions can be made easier with the knowledge from this unit. We've talked about, buying cars and houses and credit cards and all kinds of stuff. Sometimes it's as simple as picking what bank account we want. So, which is better? You have $2,000 and you want to invest it in bank A with an interest rate of 4%, compounding daily, or you can invest that same $2,000 in bank B with an interest rate of 4.05% annually. So the rates are different. One's annual, one's daily. You cannot always take the highest interest rate. You need to compare. Now, there's no time on this. You could pick a time. Let's see. Let's say 3 years. Let's check it, what you're going to make in 3 years. Okay. So at Bank A, using your formula that I will put right here, A equals P times 1 plus R over N to the N times T. Okay. So Bank A, don't want to confuse our A's here. Your total balance at the end of 3 years is going to be that $2,000 that you initially invest times 1 plus 0.04, because that's that rate. Daily is 365. 365 times 3 years. We put that into our calculator. At the end of 3 years, we're going to have $2,254.98. At Bank B, at the end of those 3 years, the same $2,000 investment, but now we have a 0.0405 interest rate. And it's annually, so our number of times per year is 1. And we plug this into our calculator, we see that we're going to have 22,000 or 2,200, excuse me, 52 and 97 cents. Which bank do you want to invest your money in? Well, it's not a big difference, but you make more money with Bank A. Even though it was a slightly lower interest rate, because it was compounding daily, you are going to make more. So you're going to choose Bank A here since you're going to make more. Okay. So that is it for Unit 3. I know you probably have some questions, so remember that you can check your textbook, you can check those references in Blackboard, you can ask the Math Center, you can ask me, you can always email or join office hours. Remember too that you don't need to waste your brain power or don't need to stress out about the formulas. Look at the formula sheet, it's in Blackboard. You're going to have that formula sheet on your test. I have put it there, you will have access to it, okay? Do not memorize the formulas. You do need to be able to look at that formula sheet and know what to use when and where. I'm not going to specifically say use this formula for this problem, but you do have the formula, so just know what you need to be able to reference. It's a good idea on these problems, especially as they get more complicated, to list what you know. If you list what you know, you're quickly going to be able to see, narrow down the formulas that you need and figure out exactly what you need to solve for what you're looking for. As a final reminder, please remember that P is always going to be the earlier time point and A is always going to be the later time. That might be past and current. That might be current and future, okay? So it just depends the context. P is earlier, A is later. It's not always going to be future, okay? Thanks again for tuning in. Go ahead, make sure that you check your course schedule for anything that might be due. And certainly use your resources. That's the end of a unit, so go ahead and start studying. Use all your practice materials, and I will talk to you guys soon.